Before we do some practice problems with the central limit theorem, I want to review this flow chart one more time. So if you're working with averages and trying to head towards a sampling distribution, your first step is to look at that population distribution and decide if it's normal or not normal. So if it is normal, you can use any sample size and go on your merry way. If your original population is not normal, then you need to make sure you have a sample size of 30 or bigger. And that's where that central limit theorem is going to come in. And then you'll be able to use that sampling distribution. So I have two problems for you to take a look at here. The first one is on gypsy moths. The gypsy moth is a serious threat to oak and aspen trees. The state ag department places traps throughout the state to detect the moths. When traps are checked periodically, the mean number of moths trapped is only 0.5, although some traps have several moths. So this means the distribution of moth counts is finite and strongly skewed with a standard deviation of 0.7. So you're going to want to address why the central limit theorem works here. And then there is a question to find a probability using that Rossman chance app. And then the Blue Mesa Fish Hatchery. A large tank of fish from a hatchery is being delivered to Blue Mesa. The hatchery claims that the mean length of the fish in the tank is 15 inches and the standard deviation is 2 inches. So again, you'll have to justify why you can use that sampling distribution, and then there are some questions to answer based on these. So I'd love for you to go ahead and pause the video and give these two problems a try. All right, so the first problem with the gypsy moths, we do have a little bit of an issue here because it does state that that distribution is strongly skewed. So that's going to be a big concern. It means we have to think a little bit more before we jump into that sampling distribution. And this is a case with a sample size of 50 that's bigger than 30. And so the central limit theorem is going to kick in here, and that's what's going to tell us we can use our sampling distribution is that sample size. So the mean will still be the original one, 0.5, but the standard deviation of 0.7, we need to divide by the square root of 50. And that gives us 0.09. So I'm going to put both of these into Rossman chance here and scale to fit. And then we have find the probability that the average number of moths in 50 traps is greater than 0.6. So I'll put 0.6 in for X, and then I want to know the probability it's greater than. So this is not the correct side that's shaded. So I'll click the inequality and flip that over. And so that probability now that the average number of moths in 50 traps is greater than 0.6 is going to be 0.1333, or about 13%. All right, so the next one on the hatchery fish. A large tank of fish from a hatchery is being delivered to Blue Mesa. So how do we know, or what do we need to know about the population before we can attempt this problem? Is that a reasonable assumption to make? So we would need to know that the lengths of the fish are normally distributed. And if we think back to chapter 3, one of the properties of the normal distribution is that it represents biological characteristics like this really well. So lengths of fish are normally distributed, and that's what's going to allow us to go ahead and use this sampling distribution. So it says if a single fish is randomly chosen from the tank, what's the probability that it'll be between 14 and 16 inches? So I'm going to put our original population distribution in of 15 and 2 and scale to fit. And then I'm going to put 14 and 16 in here. And so what we get is that the probability that fish will be between that 14 and 16 is about 38%, 0.3829. And now what if we pull a random sample of 9 fish? So we'll still have the same mean, still have normal, but now we have to adjust that standard deviation. So 2 divided by the square root of 9 will give me 0.67. And so now the probability that those 9 fish will average to a number between 14 and 16 inches is about 86%, 0.8644. So that probability is getting bigger. And then one more, a random sample of 36 fish is taken from the tank. So we need to recalculate the standard deviation again, 3 divided by the square root of 36. So it gives me 0.33, scale to fit. And now the probability that those 36 fish would average to a number between 14 and 16 inches is 99%, 99 or 0.9976. So what happens is as that sample size increases, all of these values are piling in towards the center. So you're getting things much more tightly clustered. And so there's much less left in the tails there.